In this video, we're gonna prove the strong Nullstellensatz. So, suppose a K is an algebraically closed field, and I is an ideal in the polynomial ring over K with n variables. We claim that if we take the zero set, the common zero set of all elements in I, and then take the ideal of all functions vanishing on that common zero set, then what we get is gonna be the radical of I. An example we took in the previous video is the ideal generated by x cubed inside the polynomial ring in one variable. The zero set of that is just the set consisting only of the element 0, and the ideal of all functions vanishing on that is the ideal generated by x, which is exactly the radical of this ideal x cubed. Alright, so let us now prove this statement. Now, containment in this direction is simple because if f lies inside the radical of I, that means some power of f is gonna lie in I. That means some power of f is gonna vanish at all zeros p of I. This means that fp to the n is gonna be 0, but fp takes value in a field, so this means that fp itself must be 0. Thus, f vanishes at the zeros of I, and therefore f lies inside the ideals of all functions vanishing at the zeros of I. Thus, we see that the radical of I is contained inside I of v of I. Now, let us show the reverse inclusion. So, let's suppose that f is a polynomial in this ideal, i.e. f vanishes on the set of common zeros of the element in I. We want to show that f actually lies inside the radical of I. Now, by Hilbert-Basis theorem, we know that the polynomial ring is Noetherian, so in particular the ideal I is finitely generated. Let us call its generators g1 to gn. Thus, by hypothesis, we have f vanishes on the set of common zeros of this gi, and we want to show that some powers of f is gonna lie inside this ideal generated by these gi's. Here we're gonna use something called the Rabinovich streak. The idea is to adjoin an extra variable y to our polynomial ring, and then consider the ideal generated by these gi's together with the element 1 minus y times f. We claim that this ideal does not have any common zero inside the affine n plus 1 space. That is because any element that is a common zero of this must first of all be a common zero of the gi's, and therefore it's also a zero of f. If so, then it cannot be a zero of 1 minus yf. So this ideal does not have any zero, and thus by the weak Nullstellensatz, this cannot be a proper ideal. This is because if this ideal is a proper ideal, then it must be contained inside some maximal ideal of the polynomial ring, and by the weak Nullstellensatz, every maximal ideal must be of this form. In particular, the elements in the maximal ideals are gonna have a common zero, and so if this is a proper ideal, it must have a non-trivial zero set. Its zero set cannot be empty. So since its zero set is empty, we know that this cannot be a proper ideal, and thus it must be the full polynomial ring. In other words, we should be able to write 1 as the combination of these gi's and 1 minus yf with coefficients in this polynomial ring. Note that these coefficient polynomials here are in the variable xi and y. Now, this is an identity as polynomials, so we can plug in for y the function f inverse, which would then cancel this term, and thus we can write 1 as a combination of the gi with coefficients being polynomials fi, right, in the variable x and together with f inverse. Now clearly each of these polynomials is going to be of the form some polynomial in x divided by some power of f, and because there are only finitely many of them, we can choose the same common denominator f to the n. Thus we can write 1 as a combination of gix over f to the n. Multiplying both sides with f to the n gives us that f to the n must lie inside the ideal generated by the gi. In other words, f must lie inside the radical of I. Thus we have shown that I of v of I is contained inside the radical of I, and this concludes the proof of strong Nullstellensatz. Before we finish, let us quickly recap the idea behind Rabinovich's trick. Here what we have was a polynomial f that vanishes on the zero set of some ideal I, and we wanted to show that some power of f is going to lie in I. So what we have is that the zero set of f contains the zero set of I, or equivalently, the set of non-zeros of f is disjoint from the set of common zeros of I. Now what Rabinovich did was to push everything into a higher dimension by introducing a new variable. So he pushed this set of non-zeros of f here into this higher dimensional version, which is now an affine variety. And he also put the zero set of I into higher dimension. And since these two sets here are disjoint, their higher dimensional versions are also going to be disjoint. But the advantage of looking at them via this high dimensional viewpoint is that this set here becomes an affine variety. So this intersection is also an affine algebraic set. Namely, it's the set of common zeros of these polynomials. And now by the weak Nullstellensatz, the fact that this affine algebraic set is empty is equivalent to saying that this ideal is not a proper ideal. And thus we can write 1 as a combination of fy minus 1 and the generators of this polynomial, and we can proceed as before.